Okay, we'll get started. So we left off, let's see, this is page 12 of chapter 6 worksheets. And we went back and we reviewed a little bit of the end of chapter 3 when we did the moles to particles calculations. So that was kind of to review what moles are about. Moles are just like a counting number. So they give us a number ratio. We can get that number ratio from the formula. And I think we started out with things like the number of hydrogens to the number of oxygens, comparing that to the number of water molecules, that kind of thing. We can also get that mole-mole relationship, that number ratio, from the chemical equation. So this middle piece right here is the mole-mole relationship, wherever it comes from. So it's moles on top and moles on the bottom, has the same unit, and we use that mole-mole relationship to change the label. We'll change the label from one thing to another, from one chemical to another chemical, or it could be from one element to the compound. So anything that has a number ratio that's fixed like that, we can use for that mole-mole relationship. We also had done some work with the molar mass. So we're going to sandwich that mole-mole ratio in between the molar masses. And that was how we went from grams of one thing to grams of a different thing. So grams to moles, moles to moles, moles to grams. And anytime you work through a chemical equation, you'll need to be in moles to cross those columns or to go to the other side of the arrow. So I'll leave this example 5. Shows what we did. And there was a little bit of, it's given in milligrams, and I just changed that into grams right away. But then in example 6, I just started that one, and I asked you to work on it. But I wrote the wrong number down here. 231.55 is the correct mass, but on Friday I wrote a different value. So I'm going to erase this stuff because now it's the correct number. So I'm going to fill in that number, right? Oh, that unit's wrong too, right? Mm-hmm. Looks like I was kind of rushing to finish up. So I need to cancel out grams of Fe3O6 to cancel here. And then I'm going to moles on top. So that's where I had done the side calculation. So 231.55 grams of Fe3O4 is 1 mole of Fe3O4. Then we're going to cancel that out by putting moles of Fe3O4 in the denominator. And we're going to change the label. So we want to change it to iron. We'll do that using a mole-mole relationship. And in this case, we're looking at the formula there. So I see there are 3 iron for every 1 of those compounds. All right, then we have to cancel out moles of iron because I don't see it over by the question mark. I'm looking for grams. So I'll introduce grams of iron on top. And we have to find that on the periodic table. So now we know what to do. Now we're going to multiply everything on the top, divide everything on the bottom. And our initial value, that 1,500 grams, gives us just 2 significant figures. So we can use this same process. We basically have looked at, in this case, there were 3 iron times the mass of iron over the total mass. If we don't have that starting mass, we could just say, let's take a 100-gram sample. It's easy. We'll just weigh out 100 grams of our substance. And using that, we can find the mass percent of an element in a compound. So earlier we looked at a mass percent concentration has a different unit and label. So that is percent of one component of a mixture over 100 grams total. So maybe I'll just write that out here. This one we would have grams of one thing over 100 grams total mixture. Now we're going to be looking at the percent composition in a pure substance. So we're looking at the elements in the compound. So we can always just assume that we're going to weigh out 1 mole. If we just weigh out 1 mole, you know how much that is, right? If it was Fe3O4, that would be 231, right? That number, yeah, there it is. You would just weigh out that much. So we can calculate that by taking the mass of each individual element and dividing by the total mass. And we'll just assume, let's just take 1 mole. And we know how to take 1 mole of a substance. We'll just calculate how many grams that we'll measure out in the balance. So it really connects to reality very directly. Now that total mass is the grams of calcium carbonate, assuming we took 1 mole of calcium carbonate. Right, on that last one, we'll take 3 of those oxygens. I guess I can just round that. I'll go ahead and round that. 0.96. So we expect this to add up to 100%. Sure that you remember to distribute those parentheses. That is the end of this section. I think that the mass percent in a compound generally is a little bit easier than these mass-to-mass calculations. But it's a good idea to be practicing those because if you have a struggle following the calculations, the way it's shown with dimensional analysis or going from mass of one thing to mass of another, that's something to keep on practicing. And we'll do it in lab. I think that's where we really understand it the best, is when we've done it in lab a little bit. We will move on to the next section, which is reactions. So some of this we've seen a little bit before. For example, we talked about the evidence of a chemical reaction. So bubbling coming off of that strip of metal. And you can see that in one of the videos for our lab, the chemical reactions lab. This next one, B, is forming a new solid. Those solutions are coming together and forming new, very fine particles that are yellow. And then that last one is releasing a bunch of heat and light. So these are signs that there's a chemical change taking place. Let's see, we talked about chemical equations, rearranging the atoms to completely destroy our original materials and produce something new. And we talked about 4 states of matter: solid, liquid, gas. And then aqueous means dissolved in water. So we're going to go a little bit deeper into what aqueous solutions require us to think about. All right, so when we have our chemical equation, we have 2 important components. And one is the coefficient, and that tells us how many. So like in this picture up here, these are the coefficients. takes 2 of those hydrogen molecules with 1 oxygen. We don't have to write the 1. And they're going to rearrange and form 2 water molecules. So the coefficients are the things that we change while we're balancing. The subscript tells us what the formula is, the chemical formula of the products. So water is H2O. We can't go H2O2 and say it's the same thing. We can't just change that subscript. It's a different compound. Okay, so let me just take a moment to show we are on the worksheets that are labeled 7, 8, 9. This is chemical reactions. So under course resources, this would be worksheet number 8. When we're writing reactions, first we're going to form neutral compounds, and that gives us the subscripts. Then when we balance, we cannot change the subscripts. All right, so we are going to basically be looking at conservation of mass. So we have the right number of elements on each side of the arrow. So the arrow is like the equal sign, and we're going to make sure that we have the right number of each element on both sides of the equation. And we're only going to change the coefficients, not the subscripts. Generally, if we're looking at the periodic table in my little cartoon form, we're generally going to start on the metal side, like a line here, and we're going to move this way. We're generally going to balance left to right. So a lot of times we'll start with metals, polyatomic atoms, hydrogen, carbon, then oxygen, and anything else. Now, that's not a strict rule. This is often just trial and error. But my goal is to help you do trial and error in a way that gets you to the answer directly. Here's our example. We have a methane, a CH4, and we have an oxygen, and those are going to form CO2 and water. This little arrow means heat. Because I know this is a combustion, I know that I can start with the carbon. Then I'm going to do the hydrogen, and then last I'm going to do the oxygen, because oxygen is by itself. So whatever I do with the oxygen, I can always fix it up at the end. So I'm going to start with a carbon, and that is a 1 and a 1, so that one's okay. It doesn't help me. Here we've got hydrogen. I might write it here. Here I've got 4 hydrogen. The arrow is my equal sign. And here I've got 2, and I need to multiply it by something. So I'm going to multiply it by 2 to make it equal to 4. So now the hydrogens are balanced. Next up, I'm going to look at the oxygens. Now, every time I put a number in front here, I'm going to get 2 of them. So I'm going to write 2x, where I'm solving for x, equals, and then this is one way I keep track so that I can find my mistakes quickly. So carbon dioxide has 2 oxygens, and here I already put a 2 in front, so I have 2 water molecules, and each one has its own oxygen. So there are 2 oxygen from the water. So solving for x, I get x equals 2, so I put a 2 in front here. So the balancing coefficients are 1, 2, 1, 2. You don't have to write the 1, but when we've got those big blank spaces, it kind of looks like it's more complete when you write them, but it's optional. Okay, so here are some practice. Let's see, let me just highlight the things. So ideally, if you've done a little bit of practice already, so if you're reading ahead and you do the problems in the book, those examples as you're reading, then maybe you have a little bit of practice. If not, you may not catch all the details, all the tricks I want to show you. But I want to show you what I call the 2-3 mismatch. So here oxygen has 2, and here oxygen has 3. There's only one way to get those equal. So when I see that there's only oxygen in one compound on each side, one has 2 and one has 3, then I want to lead off by saying, okay, I must need 2 of those and 3 of those to get 6 equals 6 for my oxygens. So I'm looking for, it's almost like cross multiplying, right? Like the crossover method. Then we have to go back and fix up aluminum. Here we had 2 times 2 is 4 aluminum. All right, notice on this one, hydrogen does that same thing. So if you can lead by balancing the hydrogen, the other things will fall into place. When I get my hydrogens balanced, then I have 2 nitrogen on the product side, so I just need 1 nitrogen molecule for that reaction. Now in the next one, we've got a single reactant with heat. So that's typically a decomposition. A lot of times we're going to need 2 of those molecules to interact, and then they fall apart. So they decompose into smaller pieces, and these can be a little more tricky to balance. So let's see, what will I start with? Oh, I better start with the metals on this one. So going left to right, sodium, and then maybe I'll take a look at the hydrogen. Oh, let's do the carbons next. Oh, here's a carbon, here's a carbon, so those are okay. No changes for that. Now let's do hydrogen. We've got 2 hydrogen, and oh, 2 hydrogen. Okay, that one's done. And then last, let's take a look at the oxygen. We've got 6 oxygens on the reactant side, so that equals 3 plus 1 plus 2. Okay, that's balanced too, so these are all 1s. All right, the next one is a little bit tricky as well. So how shall we start? Calcium is 1 to 1. So let's start with the chlorines. And that will get me a 2 there. Calcium, I've got 1 carbon, 2 hydrogens, and then I've got oxygens. I've got 3 equals 1 plus 2. So everything else are 1s. In the next section, we're going to use polyatomic ions, and they are exactly the same in terms of balancing. Now, the thing with polyatomic ions is it's nice to treat them as a unit. Here we can see, for example, with the nitrates, we've got 2 nitrates and 3 nitrates. So that's probably where I'd want to start balancing that one. Oh, the computer's being a little slow. I'll let it catch up. So go ahead and balance these. The only thing, let's see, what's going to be different here. Here's what's tricky here. Is let's think of the water as an H with an OH, because then you could think of that hydroxide right there. All right, and then we can check our metals, and those look balanced. There's another way to think of this one also. When we think of this ionic compound, the potassium nitrate, that requires that we have 1 potassium with 1 nitrate, because it's a K plus with an NO3 minus. Here I've got 3 K pluses. Here I've got 2 NO3 minuses. So if we think about those combining, the minimum number of KNO3 formula units is going to be 6. So if that's not obvious to you, that's okay. You just need a little bit of practice. It's just another way to look quickly at what's going to be the minimum. So from there, everything falls out. But you could also start with the metals in this case. Right? It's just an iterative process. Same thing here. You could think of 2 hydroxides and 3 hydrogens coming together to form a minimum of 6 waters. Or you can start with the metals. All right, so we're going to translate each word equation into a chemical equation and balance it. So this is what you're doing in the post lab for chemical reactions. Quick review. How does hydrogen come as an element in nature? And then water, what's the phase of water? What's the state of matter? Water implies a liquid. Maybe we would have steam or we would have ice. Okay, then we need to balance it. And then we're all set. How does sodium metal look by itself? It's just one atom in the solid. That's how metals come. Just one atom. And they're all solid except mercury. All right, what about chlorine gas? That one is a diatomic. Now, what's the neutral compound, the smallest neutral subunit of sodium chloride? Well, we'll start with the formula. Na plus Cl minus, it's a solid. Now, because there's two chlorines, I need to form two of those, and that will require 2 sodium. All right, one more.
All right, Professor, how do we know there's 2 chlorines?
Chlorine comes as a diatomic gas. Do you remember the diatomic 7?
Yes, yeah.
Yeah. Oh, that's up at the top. Plus hydrogen. So chlorine is one of those members of the diatomic 7. So just quick review. Yeah, good idea to point that out. All right, zinc is another metal. What does hydrochloric acid look like?
So HCl.
That's right. And acids are always aqueous. Yeah, that's right. Acids are always aqueous. They grab water. Okay, we're going to produce hydrogen gas. That's one of our diatomics. And then aqueous zinc chloride. So we need a neutral compound for zinc chloride. Zinc always forms a +2, and chlorine always forms a chloride -1. So we know the relationship between the zinc and the chloride just from those rules on the simple ions. Okay, now we have to balance, and we need 2 hydrogens and 2 chlorides, so we'll just use 2 of those. So now you have everything you need to do the post lab for chemical reactions. You're going to watch videos and take observations, and it's all just doing problems like this. They give you words, you write the formulas, and balance. Next up, we're going to do some specific kinds of reactions. Oh, right. So we're going to talk a little bit more about aqueous solutions. And that's why there's some reading assigned from chapter 13, which is where they talk about solutions. So we're sort of weaving that in together. When we have a solution, what we really mean is a homogeneous mixture. We could have a homogeneous mixture that's a liquid or a solid. So for example, jewelry metal, they'll melt it down to make an alloy, stir it up, make it evenly mixed, and then cast it into hard jewelry. So it looks all the same, but it's actually a mixture in there, like an alloy. So whenever you have a mixture, you have something that's present in a small amount. That's usually what we care about. For example, if we talk about lemonade, we name it for the main thing we care about, the flavor of lemon. But it's probably just sugar. I mean, it's sugar, right? It's water with sugar in it and a little bit of lemon. So there's a solute that we're interested in. Maybe there's multiple things in there, but we often name it for the solute that's present in smaller amount, but the one that we care about. And then the solvent is the thing that's present in the greatest amount, and that's usually water for biological systems. Okay, so if we take a look at saline solution. Okay, so the solute here is NaCl, and the solvent is water. What about carbonated water? It's got CO2 gas. Well, in that case, the CO2 is the solute, and the water is still the solvent. So that counts. So a little bit about how solutions form. And I think we've seen this before because we were just getting into the intermolecular forces. Like, how do these things form? We have our salt crystal in this case, and we see that the charge attraction, the positive ion and the negative ion are attracted to each other, but when they have a lot of interactions with a solvent that stabilize them, they can actually float away. So you see all that yellow glowing is where that ion dipole interaction has stabilized the ion. So it's able to move freely in water by itself. And that works for negative ions and for positive ions. So many ionic compounds will dissolve in water. For something like salt, if you think about at home, you just take a clear glass of water, and you pour salt in it, stir it, it disappears, right? We don't see it. When we write sodium chloride aqueous, we really mean that's the same thing as saying Na plus aqueous and Cl minus aqueous. They move independently. So they're really floating around. Aqueous, dissolved salts move around independently. They allow those ions to flow.
Like salt and sugar dissolve more easily when the water is hotter. Like sugar dissolves in tea much better than it dissolves in lemonade, for example.
Yeah, that's an interesting question. And they're different. So usually it has to do with kinetic energy, having collisions, transferring that heat quicker. They're moving faster, so they have more collisions. Typically, that's what's going on, and we're going to look at that in chapter 14, I believe. This is the temperature down here, and this is the grams that can dissolve per 100 milliliters. Salt looks like that, and sugar looks like that. Right, that's that C12O6H12, something like that. Sugar has a really big difference in solubility with temperature, whereas salt doesn't change that much. So again, it's empirical, it's observed. So we don't just know from first principles. But that's a good point, and we'll look at that. Now the next section, as we get into ionic compounds that do not dissolve, we're looking at two aqueous ionic salts here. That means for both of these, those ions are floating around independently. So there's two K pluses and two I minuses, and they're just bumping around in solution. For the lead nitrate, there's one lead 2 ion and two nitrates floating around independently. When these come together, we pour them together, they're both clear and colorless. That lead gets together with the iodine, and it forms lead iodide solid. It no longer dissolves. It forms an insoluble salt, and lead is one of those elements that makes everything insoluble. Not everything, but a lot of stuff that would otherwise be soluble. So that's our precipitation reaction, and you see that yellow solid, that is the lead 2 iodide, precipitate. the next section we're going to take a look at is using the solubility rules. This is a very compact list of rules that were found empirically through lots of experiments, and they're ordered in a very particular order so that you can quickly work through what's known, right? So there's nothing super fundamental about it. These are observations that are collected and organized in a way that we can use them. There are still exceptions, but they're very well done. Solubility rules will help us predict what is going to be solid and what's going to be aqueous. So I like to keep using the words aqueous and solid. I like to do that because if I say soluble and insoluble, I just get really tangled up on the words. This is how the solubility rules work. They're ordered in importance. So when you have an ionic compound, you're going to look for those two ions. And the first one you meet, that's it, you're done. Okay, so if it's on the left side of the chart, these are going to be soluble. This side is aqueous. This side is solid. So if you have anything that has lithium, sodium, potassium, or ammonium, it's aqueous, you're done. So we'll go through these in order, and let me copy one of these. Let me copy AlCl3. There's none of the rule number 1 items. There's no acetate, there's no nitrate. Oh, there's a halogen. And there's an exception. So an exception on this side means that it would be solid. But that is silver, lead, and mercury. We don't have that here. So now we know our answer, right? This is going to be aqueous by rule number 3 for halogens. Okay, so we apply them in order, and we'll assign aqueous if we meet that ion on the left side. If we get all the way to rule numbers 6 through 10, then it would be solid. Strongly recommend that you try and get ahead in Alex. Okay, have a great day. I'll see you guys later. And these, you can always find these on that link in the forum. Worksheets and 0365 has the answers on there.